Reservoir simulation and reservoir adaptation take a long time and use a lot of our computer resources, which is something we all know. There are also many works have been published on the topic of using machine learning methods to speed up either the simulation process or the adaptation workflow, and some of them I published on this channel. But just think about it. There is too much sense to couple those workflows together, simulation and adaptation. Hello, my name is Ruslan, and today I talk about machine learning based framework that can substantially speed up conventional simulation and adaptation workflows. And there is much more into that. The code of this work is also available on Github as well. The link in the description. Subsurface fluid dynamics are the focus of reservoir simulation, which aims to provide evaluation of pressure and saturation within reasonable error bounds. On the other hand, reservoir adaptation, aka history matching, change initial and boundary conditions to make sure that the simulated data matches well with real well production. This is a nil-post problem that demands the use of various strategies for adaptation. A unified strategy for reservoir simulation and adaptation is presented in this work. They use neural network, which is not surprising, but they use only one neural network for both of these processes. Let's begin by getting our heads around the reservoir simulation, and then we'll do the history matching. This suggests proxy modeling way that combine machine learning methods and ordinary differential equations. The aim is to use encoder neural network to translate the reservoir dynamics into a latent space. The latent space is a condensed representation where non-important features are removed from consideration, and then use an ODE to reconstruct the reservoir dynamics from the latent space into a reservoir grid. In this context, ODE refers to a nonlinear function that, to those experienced in machine learning, will look and feel like a complex activation function. In other words, the encoder's purpose is to map a highly nonlinear and difficult problem to less complicated ODE. And the decoder's responsibility is to exploit the loan relationship to reconstruct a true simulation-like forecasting. And this is how they did the training. They used several real oil field reservoir models as their starting point, randomized reservoir parameters with well controls, and then performed reservoir simulation using a traditional finite difference reservoir simulator. And using a collected output from this exercise, they trained this network. Okay, we've seen that the forward pass across the network behaves as reservoir simulator that helps us to obtain production rates. Now let's consider what happens in the backward pass and history matching. Backward gradient propagation can be done on any neural network, and since the input variables in our case are based on reservoir and state variables, using historical well data and a production rate estimated by the network, we may compute a misfit function at a given time step and then propagate the changes to reservoir variables and build an optimization procedures around them. Consider the testing experiment that ties it all together. A synthetic oil field model which has roughly 1.3 million of active cells and free-phase fluid. The model is challenging because of complicated geological structure with both gas cap and water contact, and due to challenging physics because of water and gas cooling effects. Because of that, the modeling accuracy is extremely important. The figure here shows a comparison between the target and predicted cumulative production rates. You can see a boundary between the simulation and adaptation phases. The prediction for those two time periods is very consistent with the target. Let's take a look at the result on the test well. The predicted value for the water production are only partially accurate. The authors talk about this problem in terms of the fact that the neural network model can only handle the features and events that are listed in reservoir history data. Obviously, the proposed network will not be able to replace state-of-the-art finite different reservoir simulation software. The network provides faster approximation at the expense of some accuracy, as in the case with any proxy simulation. If you want to learn more about deep learning in reservoir simulation, take a look at this video to see how deep learning can speed up geological carbon sequestration simulation 250 times. If you are the author, or you know an interesting and open ML paper in oil and gas, get in touch with me. See you at the next one.